involving reaction that heads in both directions. So when we have the forward direction that occurs, at some point you will build up enough of these products here that they will start to combine and head in the opposite direction. And again, that is what's known as the reverse direction. It will continue in this path here until, as we talked about, it reaches chemical equilibrium. And remember that when we talk about equilibrium, we're actually talking about rates, and it's the rate of the forward direction will eventually equal the rate of the reverse direction. So remember that equilibrium doesn't mean that you have the same amount of everything on each side. It just means that the rate of those reactions, the forward direction and the reverse direction, will essentially equal each other. What that will do, as we talked about, is essentially lock everybody into place in this reaction in terms of their concentrations, or if you're looking at pressures, also their pressures as well. So they basically will be able to maintain where they're at once it reaches equilibrium. And there is a relationship that we could write for a reaction like this, which is known as the capital K there, which is the equilibrium constant. And the equilibrium constant is a constant value at a particular temperature. So temperature is really the only thing that can change the actual value of the equilibrium constant, but it will be the same value as long as you keep the temperature the same. So as we talked about, I think in an example last time, you could do the same equation or same reaction 4 different ways. You could start with all reactants, thank you, all products, a little bit of everybody. And it will always come to the same ratio of products to reactants. It gives you the same value of K as long as you don't change the temperature. So the way we do calculate K is we do basically the concentration of our products divided by the concentration of our reactants. And so, for example, here we would write K is equal to C, and we do need to take the coefficients in the balanced equation as the exponents. So we would cube it in my example up there. D would be squared because of the coefficient. That would be divided by A, which would be squared, and B, which will just be to the first power there, as we don't have any coefficient there, which is a 1 basically. This, where we actually use concentrations in this equilibrium expression, is sometimes referred to as the Kc value, C for concentration, basically. We also, for example, in this case, if they were all gases, like I sort of wrote here, if these guys were all gases, we could also write an equilibrium expression that deals with pressures, since that is something that we would oftentimes look at if we're dealing with gases. And it works the same way. It would be the partial pressure of C cubed times the partial pressure squared of D divided by the partial pressure squared of A and the partial pressure of B, which is basically to the first power. And you could do really the same sort of relationship. And since here we're using pressures, this is sometimes referred to as a Kp value, P for pressure. So you can actually do that. By the way, if you do that ever, usually atmospheres is the unit that you want to roll with in pressures. And obviously here, molarity is typically the units you want to roll with, in terms of Kc. So Kc, Kp, they're really just all equilibrium expressions. The little subscript doesn't matter. In fact, we actually already saw an equilibrium expression, and that was when we were doing the previous chapter, Kw, which is our H plus and our OH minus equals 1 times 10 to the minus 14, and that's off of water basically dissociated into H plus and OH minus. So that Kw that we saw earlier in that previous chapter is also an equilibrium constant, and it's an equilibrium expression. There's all kinds of Ks, as we talked about. I think when you take 1B, you'll learn about every single K you never want to know about. But ultimately, they're all pretty much the same idea. They're all basically the ratio of the products to reactants. And remember that K is one of the few things in chemistry that we don't have units for. But if we do have a large value of K, what that tells us again is when we reach equilibrium, we would mainly expect to have products present. And again, it's just math here. To get a large value, up on top would have to be a large value, and up on the bottom or down on the bottom would have to be a small value. If you have a small value of K, then it means that when you reach equilibrium, you mainly have reactants sort of present. And again, a large value of K is considered 1, basically. So anything sort of above 1 is considered a large value of K. Anything less than 1 is considered a sort of small value of K. When we do write these equilibrium expressions, there are a couple of things that are not included, and there are some things that are included. So when we do write this, we do include only things that are in the aqueous state and things in the gas state. So those are really the only things that get included in these expressions. We do not include anything that is a solid or a liquid. And the reason for that is solids really, if you just think about it, are just hanging out. They're not really participating in any type of reaction. They're just kind of sitting there. The only way really for a solid to participate is it would have to dissolve. And at that point, it's no longer a solid. It's basically aqueous ions floating around, which would be included at that point. And liquids like water, for example, their concentration is really, really large, which means over the course of the reaction, it doesn't really change all that much. So it stays relatively constant as well. So really anything that's aqueous, anything that's a gas would be included in this. Anything that's solid or liquid, you would exclude from it. Any questions on any up there? So a reminder, if we look at these, and I can't remember if we went over them or not, but we'll go over them right now just to make sure. A homogeneous equilibrium, again, homogeneous equilibrium means that basically everybody's in the same phase, kind of like a homogeneous mixture. Everything looks the same throughout. So here, everybody's in the gas phase, so we can, again, write a Kc value for this, and we're going to take our products, which is our NH3. We do need to square it once again for the coefficient that is there. We divide it by the concentration of N2 and the concentration of H2, and again, that would be cubed for the coefficient. Obviously here, again, that's a 1, so you don't really need to write it. It's assumed, obviously, if you do not see anything up here, that that is obviously a 1 in this case. In this particular case, because they are gases, we could, if we wanted to, also write a Kp expression. Once again, works the same way, just the partial pressure squared of NH3 divided by the partial pressure of N2 and the partial pressure of H2, which would need to be cubed in this particular case. On the bottom one here, we got, again, our Kc, which is our H plus, our Cn minus, divided by our HCN. Bottom one, we can't really write a Kp because there's no gases. So you need some gases, right, to cause pressure. And since there's no gases, obviously you can't have a Kp. Any questions on those there? Now, obviously, these are all in the same phases, but you definitely can get a mixture of sort of phases that occur. And in that sort of mixture of phases, that's sometimes referred to as a heterogeneous equilibrium. Heterogeneous, much like heterogeneous mixtures, where you see different phases. Same idea here. So you can see here, we have some solids, we got some gases sort of happening in the same equilibrium. So if we were going to write the equilibrium expression here, this would be our Kc is going to be the concentration of O2, and we would cube it in this case. This is a solid which would not be included, and this is a solid which would not be included either, and that would be our entire expression in this case. Because that actually is a gas, you could write a Kp in this case, which would be the partial pressure of O2 cubed. Any questions on that one there? Yeah. For our purposes, in most cases, it really has to do with the information given to you. So if you're given concentrations, then Kc is typically what you'd use. If you're given pressures, which is commonly can be done because you can do equilibrium with pressures, then probably the Kp value. And you may be given, for example, a Kp or a Kc value in a problem, And it doesn't really matter, the little symbol, but that's usually what you would use based on sort of information given to you. Yeah. Other questions? Here on the bottom, there we go. Here on the bottom, here we're going to go with our Kc is our H2 squared and our O2 to nothing. Once again, this is a pure liquid, so it will not be included. And again here, you could do a Kp because you do have some gases, so partial pressure of H2 squared and our partial pressure of O2 in this particular case. By the way, the Kc and the Kp value usually do not equal the same numerical value, so they're not usually the same. Usually not the same uh, value, basically. They can be in a weird sort of situation. It is possible, but in most cases, they're different numbers. But they do tell you the same thing. So, for example, if you have a large Kc value, you would also expect to have a larger Kp value. And they both would tell you that you should bring you had products at equilibrium. And if you had a small Kc value, you probably would have a smaller Kp value as well. And it kind of tell you the same idea. Now, what happens if we had some situation like this where maybe, we had okay. So maybe we had some aqueous ions on the reactant side and something that's solid here on our product side. So in this case, we would write our K, which would still be our products over reactants, but since this is not going to be included and it is a product, we'd actually just do 1 over the reactants in this case. And it would be A squared and B. So if we have something on the product side that's not included, but something on the reactant side that needs to be included, you basically just do 1 over the reactants. And that's similar to what we have here. We have no reactants included, so it's basically just the product side. And again, that is what we would write in that equilibrium. Any questions on those or how to write those there? So as we talked about, the position of the heterogeneous equilibrium, put that up, does not depend on solids or liquids. And again, as I mentioned, basically those two things are just kind of hanging out. They're not really actively involved in that reaction. And the idea there, remember, is that these type of reactions are really consistently happening. They're continuously having this reaction happen, even though, as we talked about last time, that you may look at it and it looks like it's over and nothing's happening. There is a constant forward and reverse reactions happening all at once. So things, again, like solid and liquid in their current states would not have a big effect on that reaction occurring. So if we look at here, a couple of these here, we have our calcium fluoride going to calcium and fluoride. Here it would be, in this case, our products, which is our calcium ion and our fluoride ion that we do need to square. Here, this being a solid would not be included. So again, that is where our equilibrium expression should be. Particular case. So let's then talk about what happens to these reactions when you do something to kind of screw them up. So as we talked about last time, these reactions will essentially, because it's constantly happening, will basically be able to maintain their equilibrium. But there is a situation or so where you can actually mess up the equilibrium. So this thing would be at equilibrium and you have this reaction, for example, like this guy here, where it's at equilibrium, which means, again, that rate of the forward direction will equal the rate of the reverse direction. Now, you could do something to screw this equilibrium up and add a stress to the system. And what will happen is when you add the stress to the system, you will actually temporarily mess up the equilibrium. And these reactions are very good in the sense that even if you try to mess up their equilibrium, they will self-correct themselves and they will get themselves back to a state of equilibrium. So even though you do something to it, they will be able to fix themselves and get back to an equilibrium. So if this was like equilibrium position one, you would stress it out there and cause it to do some type of adjustment to get back to equilibrium number two position. Now, what will happen is this reaction, as I mentioned, will adjust. And the way that it typically can adjust is in three different ways, essentially. It can adjust by shifting to the left, which basically means you need more reactants, or you're going to need more reactants. It can shift to the right, which means you're going to head towards the products. And there are certain situations that even though you did something to it to screw it up, you will see actually no change occur. So there is a kind of no change option. So when we talk about Le Chatelier's principle, which is this principle that we're talking about of you can mess up the equilibrium, but it will try to self-correct. These are the three sort of things that can occur as a result of you doing that. Either it will shift to the right, make more products, shift to the left, make more reactants, or again, even though you did something, not much is going to happen. So what are these stresses that you can do to a system that's at equilibrium? There are a few different ones. We're going to talk about each of them individually here. But the stress that you can add to this is you could do something with concentration. So you could either add more or remove concentration. You can do something with pressure and volume if you're dealing with a gas. You could also do something with temperature. And lastly, you could do something like add a catalyst to the equilibrium here. So these are four common things that can be done to a system that's at equilibrium that will ultimately screw up the equilibrium and eventually allow this reaction to kind of self-correct itself and get itself back into an equilibrium state. So let's talk about each of these and sort of talk about what happens as these things get stressed out. Yes, sir. Yeah, so it's technically a stress that can be put on the system. And even though you kind of did something to it overall, it won't cause a change to occur in the equilibrium. The rate will basically kind of stay the same of the forward and reverse direction. We'll talk about a couple of situations where that can kind of occur, and that's in the next second. But the idea here is you still added some type of stress to it, but overall, it's not going to have really any effect on it, in a sense. So it's not enough to kind of tip it one way or the other in terms of it changing. Other questions? All right, so let's start with the first one, which is concentration. And when we're dealing with concentration, there's really two things you can do. You can add more. And when you add more concentration, the equilibrium will typically shift away from the side you added it to. So what do we mean when we say side? When we're talking about the side, we're really talking about the equation, like you look at it as it's written. And on the left-hand side are reactants, right? On the right-hand side are products. So we're talking about, did I add more reactants? Did I add more products? So that's what we're talking about when we talk about shifting away from the side that it is. So when you add, it goes away. Add away is the way to kind of remember that. When you remove something, it actually will shift to the side you removed it from. So when you remove something, it actually will go towards the side that you removed it from in an effort to sort of fix that. So how do we do both of these things? Well, if we think about it, one way is If we add more, it's very simple. All you have to do is pretty much just go to the shelf and grab a bottle of whatever it is in that reaction. So for example, if you had iron in that reaction, all you do is go to the shelf, grab something with iron in it, like iron 3 nitrate, something like that. You dump it into your beaker. You just added more iron basically in there. So adding is very simple. You could just find a reagent that has that ion in it, for example, and you could add that, or obviously, if it's a gas, you could just add more gas of it. Removing is a little bit different. So how do we remove something that are ions, for example, in solution? So just a reminder that where we find ions are floating around basically in solution. And they are the ones that are just kind of floating around. So if I wanted to remove, say, my positive ions or my negative ions, I can't just reach into the beaker, right, and grab them out because they're basically in the liquid form, right, and they're floating around. So you can't like scoop them out, right? So usually the way that we remove something is we actually will add something to that equilibrium that's not part of the equilibrium, but will react with somebody that's floating around in the beaker. So for example, let's just say we had some chloride ions in here, right? Cl minuses. Now, chloride ions are floating around in the solution. And if I decide to add something like silver nitrate, which is a source of silver, when I add that silver in there, it's going to go find those chlorides and basically it's going to cause a precipitate to form. It will cause a solid to form, right? And now that precipitate is essentially reaching in there and taking out the chlorides from the actual solution as it's floating around. And that's a very common way that you can remove an ion, for example, from a solution is you could add something else that will precipitate it out. And now because that ion is no longer floating around, it's actually a solid. It would not be included in the equilibrium, right? So again, that's essentially removing it. That is actually something that you could see happen. Another way that we could remove something is a similar process. So for example, let's just say in the beaker, you had hydroxide or you had a beaker of H plus floating around. You could add either an acid to this beaker, or if you had this beaker, you could actually add a base. Which would be hydroxide basically being added. And when we would do that, in each of those cases, it would actually make water. And this is another thing that's not included in the equilibrium. So the formation of water, you could get rid of hydroxide that's in the solution. You could also get rid of H plus that's in the solution by either adding an acid or base, depending on the situation. Although in most cases, that's a little harder one because you can't usually visually see that you made water. But you can sometimes, if it causes the equilibrium to shift, see a color change occur. But the formation of water is a one way that we could remove something like hydroxide or H plus from solution. Adding something that will precipitate out an ion that's floating around is another way that we could remove something from a solution. Any questions on that there? So what are we talking about here with concentration? Well, if we just take a look at a simple diagram, maybe we'll see. Let's go with this, my reactant side. This is my product side. And we have our classic stick figures here, advanced stick figures with faces, right? And they're at equilibrium here. So let's just say in this particular case, somebody decided I would like to hop on over here. And when they do so, again, that's going to cause this equilibrium to shift, right? And now we can see that we added to our product side to fix the situation. We need to actually shift away from our product side, right? Away from the side we added it to kind of balance it back out to equilibrium. And it will once again return to equilibrium here. And it'll get back to equilibrium. So wherever we add, it will shift away from it to reach equilibrium. Same idea if you remove, again, yeah, the kind of similar setup. This guy over here is our product. This guy is our reactant. And we'll just say this guy decided to hop off. And what's going to happen in this case is you're going to get this situation. Not so good. To fix this right, we actually need to shift towards the side we removed it from. And that's going to put it back into equilibrium. Now let's go over here. And we'll get back to our equilibrium state in this case. Any questions on that there? So when you shift, it will shift away from whatever side you added. So if you add more reactants, it will go to products. If you add more products, it will go to reactants. And if you remove something, your reactants, it will go towards it, or products, it will go towards it. When you remove, you can think about it as like you made a big hole on that side, so you gotta go fill the hole. So it wants to go towards the hole basically to fill it. When you add again, it's just gonna kind of shift away from that side in that particular case. Any questions on that there? The next thing that we can look at is pressure and volume, and they oftentimes are tied together. And pressure and volume are related to each other, and that has to do with gases, obviously. And again, if you remember Boyle's law, as the pressure goes up, the volume will go down in this case. And as the pressure goes down, that typically results in the volume going up. So these guys are related to each other. And what happens, for example, is if the pressure goes up, that means the volume goes down. And what happens is in this much smaller space, we now have all of our gas molecules really close to one another. And that's really what's causing the pressure to start to go up, right? Because we're going to have a lot more collisions occurring. So the change that's kind of occurring when we lower the volume or increase the pressure is the pressure is kind of going up. So the goal here is to sort of fix that and bring the pressure back down a little bit. And the way it's going to be able to do that is it will shift to the side with the least number of gas molecules. Now, that's really dependent on the equation you're looking at as to whether that's the left-hand side or the right-hand side. What you essentially need to do is just count up everybody that has gases, the little G symbol on the left and the right, and the coefficients, and figure out which side is more gas molecules, which side is less gas molecules. Now, the opposite, right? The pressure will go down as the volume goes up. So as the volume increases, we now have a lot more space for those gas molecules to start to move around. And the idea there is it's going to cause less collisions to occur, and that's why we see our pressure start to drop. So in this particular case, it will actually shift to the side with more gas molecules. That again is also dependent on the equation you're looking at. The idea there is more gas molecules will basically cause the pressure to go back up from going down. I personally always think of these relationships in terms of volume, and it just matches the volume. And what I mean by that is if you have a high pressure, small volume, less gas molecules. If you have a lower pressure, larger volume, more gas molecules. So it sort of matches the volume here as to which side it needs to shift in terms of gas molecules. Small volume less, larger volume more gas molecules. And that's a good way to sort of really remember it. And since the pressure and the volume are tied to each other, even if you have a question about pressure, you could just relate it to the volume and go, okay, large pressure, small volume, small gas molecules. And that's a good way to kind of remember that. Any questions on that there? So let's take a look at an example. So let's just say we had 2A plus 4B goes to, we'll go 3C in this case. So for each of these, decide what will happen. Will it shift to the right, to the left, or will there be no change if you do the following? Let's say we add more C, we remove B, we lower the pressure, we decrease the volume, and we add more A. So for each of these, which way should the equilibrium shift in this case? Okay, so let's take a look. So in this case, we're going to add more C, which is here, and C is a product. So again, we add it to the right-hand side, add away, so it should shift equilibrium to the left in this case. And again, really the reason for that is sort of what we talked about at the beginning of the chapter, which is we now have more products than reactants, and that's going to cause actually the reverse reaction basically to occur, and that's why we're going to head towards our products. If we remove B, B's over here on our reactant side. That again is going to cause the equilibrium actually to shift towards the side. Again, like there's a hole over there, you got to go fill it. So it's going to shift to the left in this case. The real reason for this is actually the same reason as above. When you remove your reactants, you again now have more products than reactants, and that's going to cause the reverse reaction to occur and head towards the reactant side. When we lower the pressure, that means that my volume has now increased. And again, in a larger volume, we actually need more gas molecules to bring the pressure back up. And on the left-hand side, we have a grand total of 6 gas molecules. And again, just adding the coefficients. Right-hand side, we have 3 gas molecules. And in this case, that means we would then shift to the left here. Again, because that is the side that has the most gas molecules. If we decrease the volume, that's going to cause a decrease in volume. That's going to cause our pressure to increase. And more important here is the volume. So again, with a smaller volume, I need less gas molecules to bring the pressure back down. In this reaction, that would cause the equilibrium to shift to the right. And lastly here, if we add more A, which is a reactant, it's going to go away from the left-hand side towards the product side. And again, in this situation, what's really happening is when we add more A, we now have more reactants than products, and that's going to cause the forward direction to occur in this case. Question? Yeah. Yeah, so you got to remember when we talk about sides, there really is kind of really no side in like the beaker or the container. But to answer your question, everybody is in the same container. So the overall pressure of that container could be um, increase. You could have like a movable kind of piston type of thing, and you could drop it down, and that's going to cause a lot more pressure to occur, and that's really where you can get your change in your volume. But yeah, everybody's in the same container, and it's kind of the same idea. We talk about right and left in relationship to the equation, but in this equilibrium, everybody's basically in there together, floating around. If it's in a solution or if it's in a gas, everybody's in the same container. Yeah. Other questions on that? Now, to answer also an earlier question, this is also, for example, a situation that you could end up with a no change occurring. And the situation I mean is when you have gases and you're dealing with pressure and volume. So let's just say, for example, that we didn't have that equation, but we have, say, this equation here. And we have 3 of those. And let's just say we have 3 of those, for example. So in this particular case, if we increase the pressure, what's going to happen is the volume will go down, right? So we want less number of gas molecules. Now with this reaction, that is 6 gas molecules still over there, but now I have 6 gas molecules over here. it's a tie, right? There is no side that's more or less. So this is one of the situations where you can get like a no change that's going to occur. And again, basically, it's just going to kind of hang out where it's at. It's not going to basically go one way or the other in this particular case. So again, that's a common place where kind of a no change situation could occur. Question on that there. So again, this would be a no change situation. Yeah. All right, so we talked about pressure and volume. We talked about concentration. So the next thing we're going to talk about in terms of Le Chatelier's principle that can affect it is temperature. And temperature, again, is a big factor that can determine what happens. So if we have temperature, the good news is temperature works the same as concentration, which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So how do we know which way is away and which way is towards it? It has to do with the type of reaction that you're dealing with and whether or not your reaction is a exothermic reaction, which means heat and energy is released. And when we have an exothermic reaction, we usually think of it as a product heat and energy. Like is be given off in this reaction. A reminder that in terms of energy, the way exothermic is usually given to you in an equation is they give you the change in enthalpy that we talked about, and it's a negative value. So if you see a delta H value for that particular reaction and it's negative, it means that that reaction is exothermic overall. And that means that, you can think of temperature or heat and energy as a product. Endothermic is the other type of reaction, and that means that heat and energy is absorbed. And we think of that situation where heat and energy is considered more a reactant in this case. So we think of it as a reactant. And a reminder that the delta H would then be positive for that reaction in that particular case. So if you have a exothermic reaction, you increase the temperature, it will shift to the reactant side. And if you decrease the temperature, put everybody on ice, it will go to the product side, and vice versa there for endothermic. If you increase the temperature of an endothermic reaction, it will shift to the right or the product side. And if you decrease it, it will come to the reactant side there on the left. Any questions all about there? And lastly here, a catalyst can also be added. And that's the last sort of thing that you can do. A catalyst actually, again, will not affect the equilibrium. And it will actually cause a no change to occur. A reminder that, again, as we talked about earlier on, a catalyst is not a reactant, it's not a product. It is there, again, just to facilitate the reaction occurring faster. It'll just get you to equilibrium quicker, but it will not cause any shift that will occur in that case. So it caused no change. Another sort of thing that can sometimes cause a no change, especially for example in a gas situation, is sometimes if you add like a noble gas in there. So if you add like a noble gas, that's like another thing that could essentially have a no change situation. Again, noble gas are chemically inert. They don't really react with anything else. They're just kind of flying around. So that's another common way. Any questions on that there? Yeah. No change. Yeah. Yeah. So that's probably your most common, I would say, in Le Chatelier's principle, no change situation. It's like a catalyst. Your second would be kind of like a tie there with the gas molecules. That's your other common places that occur. And again, occasionally books and stuff like to slip in like a noble gas or something, that's again another situation where you can't get a no change occurring depending on it. Other questions? All right, so let's take a look here. So let's say we had this reaction here. We'll do N2 plus H2 gives us NH3. 2 there and a 3 there. We'll go delta H just for this funness here, plus 325. That is definitely nowhere near the right number, but we'll go with it. So let's say what will happen here in each of these cases here. Which way will it shift, to the left or to the right, or will there be no change? If I do the following, I add H2, I increase the temperature, I decrease the volume, I add NH3, I remove N2, I decrease the pressure, I add a catalyst, I remove H2. All right, give it a go, see what will happen in this case. Yeah. So it is, so two answers that overall in reality is what you're doing because again everybody's in the same container, so overall you're increasing it, but when we think about how it's going to affect that equation, you have to determine which side of the reaction, if you looked at the equation, is it considered a reactant or product, and that's based on the type of reaction. Okay, so let's take a look. We'll start with the first one. So we're going to add some H2. So again, as we've been talking about, even though there's really no sides in the beaker, we think about the sides in terms of how the equation is written, and that's where you want to kind of think about it. So in this case, it is a reactant, and when we add, it always goes away, so AA, right? So it should shift to the right. Again, the real reason this is happening is we just added more reactants. So that's going to cause the forward direction of that reaction to occur. Because again, the more you have on one side or the other will cause that reaction to basically occur. When we increase the temperature, to answer the question here earlier, this is again in relationship to the equation and what type of reaction that's occurring. And again, I would say probably this is the most common way they'll kind of tell you whether it's exothermic or endothermic. And remember, the number is not super important here. It's actually just the sign. And in this case, since it is positive, that means that this reaction is actually endothermic, and that helps us get an orientation in terms of the side of where heat, energy, and really temperature is at. And because it's endothermic, it's being absorbed, we think of heat and energy as being a reactant in this side. So now that we have that squared away, we treat it the same way as we do concentration. So when we increase the temperature, that again is essentially like adding more reactants, and that's going to cause it to shift away from it and the forward reaction to occur, and it should shift to the right in this case. Any questions on that there? Now, if we lower the volume, that would actually increase the pressure in this case. And really here, since it's volume, that's what I would want to look at. And when I have a smaller volume, I need smaller number of gas molecules in this case, right? So that's a good way to remember. So we just need to add up what we got going on. So this is a gas molecule. The coefficient is a 1, and that is a 3 gas molecules there. So that's a grand total of 4 gas molecules on the left. On the right-hand side, we have a coefficient of 1, or 2, and that is 2 gas molecules on the right. So in this case, we need actually less gas molecules. So that also is going to cause it to shift to the right in this case, again, where we have less gas molecules. And then what we're doing here is the change that's occurring when we stress it out is pressure jumps. So we want to bring the pressure back down. And again, less gas molecules is going to allow us to do that. Next, we add NH3, which is a product. So since we're adding, it's going to go away, and it will go to the left-hand side in this case. And again, same reasoning. We now added more products than we have reactants. So the abundance of products now will cause the reverse direction to occur in this reaction, and it will head that way. Here we're going to remove N2, which is over here. And when we remove, it always goes towards it. Again, if you want to remember it, like you made a hole, you want to fill it. So it'll go towards that hole you made, and you could go fill it. The true reason is the same reason we just talked about. We actually now have, again, more products than reactants, and that's going to cause our reverse reaction to occur and head in that direction. Here we are lowering the pressure, which means in terms of volume, my volume should then increase. And again, with a larger volume, we need more gas molecules. And in this case, more gas molecules is to the left in this case. Lastly, here, adding a catalyst will cause no change to occur. And if we remove H2, which is a reactant, that's going to cause a hole on the reactant side that needs to be filled, and we're going to go towards it. But in reality, what's happening again is we have, in that case, more products now than reactants, and that's going to cause the reverse direction to occur. Any questions on any of those there? All right, so again, as we talked about, the effect on the concentration, add more goes away, goes towards it, it will remove or remove it when we go towards it, or it will shift towards it when we remove something. I'll spit that out. Here's our change in volume and really our pressure, as we talked about. And again, you could have some type of movable piston. And as you can see, everybody's in the container together. And again, it's just, you could have changed the pressure on the whole thing. But again, in terms of Le Chatelier's principle, we think about it in terms of left or right based on the equation, how it is written. The effect on volume here, again, decreasing that volume would have a need for less gas molecules and more gas molecules in a larger volume. And again, that obviously, again, as we talked about, is reaction dependent. Exothermic, endothermic, once again, that is going to help you determine are you thinking of temperature as a reactant or a product? Also, a reminder, as we also talked about, that this again is the only thing that actually affects the value of the equilibrium constant. Remember that you can have a bunch of reactions like we talked about, and you could have all reactants, all products, a little bit of everybody in one experiment, more reactants than another one, and they all should end up with the same equilibrium constant as long as the temperature doesn't change. And that was that example where I did, I think, the other day where like I want my K to be 2, and there's, again, many sort of ways that you could get to 2 by just dividing like products over reactants, and they're all different numbers, but the ratio of products to reactants always will end up the same. And that's what happens when you keep the temperature constant. Even though you're starting with more in one experiment versus the other, when they come to equilibrium, that proportion of products to reactants will always be the same. But it will differ if you look at your K value at 25 degrees Celsius, say, versus your K value at 35 degrees Celsius. And it also depends on the type of reaction as to how the value would change. So for example, if we take the reaction like this here, and our delta H is positive, which means it's an endothermic reaction, right? And in this case, heat would be a reactant. So if I did my K value at 25 degrees Celsius, right, and we'll just say my K was 50 at 25 degrees Celsius. If I increase the temperature, would my K value be higher or lower than 50 degrees? Let's say I increase it to 35 degrees Celsius. Should my K value actually go up or down in this case? We know it shouldn't stay the same, right? Because we changed the temperature. So which way should it go? So let's see. It should go up, I think. Yeah, I agree with you. So let's see. In this case, we would be increasing the temperature, which means we're adding more reactants, which is going to cause the equilibrium to shift to the products. And since K is products divided by reactants, in that difference, we are going to end up in this case with a different proportion of products than we did at 25 degrees. And that's what's going to give us our different K value. So the K value here would be correct. It should be higher than 50. And vice versa, obviously, if we lowered the temperature in this case, right, the K value actually should be less than 50 in that case, right? And the same thing sort of thing could happen if you had an exothermic equilibrium. If you had an exothermic equilibrium reaction, heat is a product. So in this case, if your K was 50 at 25 degrees Celsius, and you increased it to say 35 degrees Celsius, your K value now will go down, right? And that's because when you increase the temperature, going to shift to the left, and we're going to have more reactants than products, and that's going to give us a bigger number on the bottom than the top, and your K value actually will go less than 50 in this case. And opposite is true if you dropped it, say, to 15 degrees Celsius, your K value will actually go up because we'll be removing this, heading to the product side, causing more products. So you can make a prediction based on whether the reaction is exothermic or endothermic, what will happen to the K value if you increase the temperature or decrease the temperature because of the shift that's going to occur. And again, that sort of different proportion of products versus reactants that you get as you shift the temperature is what causes the equilibrium constant to actually change versus at 35 degrees. Any questions on that there? Okay. All right, so let's see here. Consider the following reaction. How many of these would lead to the shift towards the reactant side? So take a moment for each of them, actually decide what will happen, actually. As we know, 3 of them will do that. So, okay, let's take a look. So first one here, we're going to remove CO. So once again, in this case, we're removing a product. That's going to create a hole over there, so we got to go fill the hole. That should cause us to shift to the right in this case, which is not a reactant, so we would actually shift towards the product side. The addition of O2, O2 is a product. That's going to cause us to have more products than reactants and will cause the equilibrium to shift to the left there, away from it. Removal of CO2. CO2 is a reactant. That's going to cause a hole on the reactant side that needs to be filled. So that's going to cause the equilibrium to shift that way. Again, it's really causing more products than reactants, so it's causing that reverse reaction to occur. Increasing the pressure by decreasing the volume. So once again here, pressure goes up, volume goes down, small volume, small number of gas molecules. So left-hand side, 2 gas molecules, right-hand side, 3. That means we're going to shift towards the side with the least, and that would be 2, 3, and 4 would be the ones that would shift it to the left there. Any questions on that one there? Okay. All right. And one method for doing this is this endothermic reaction. How many of these would decrease the amount of H2 present? So let's see here. Let's take a look through these. Water is added. By the way, this is water in the gas phase, which does affect equilibrium, and it will different than water in the liquid phase, which is not part of it. Adding water here in the gas phase is going to increase our reactants and cause the equilibrium to shift to the right. And that should increase the amount of H2, right? Because that's on the right-hand side. So that's not going to do it. The volume is doubled. So here the volume went up. That means the pressure went down. So here we want to go to the side, larger volume, more gas molecules. That is 2 gas molecules on this side. And that looks like 3 or plus 1 more. Yes, 4 gas molecules on that side. And that means in this case, we're going to shift to the right, which would also increase the amount of H2. CH4 is removed. CH4 is a reactant. That's going to decrease our reactants and increase our products and going to shift towards that hole we just made there. And that would actually decrease the H2 in this case, right? Because it's shifting away from it. So that would be the one there. Temperatures increase in this reaction. It's endothermic, which means delta H is positive, and heat is a reactant in this case. And that would mean that if we increase the reactant, more reactant is going to shift away, and that would actually increase the amount of H2 in this case. So it is number 3 that would actually accomplish what the question asked. Any questions on any of those there? All right, I think we'll lay it up there, I think, for it right now.